Now let's talk about the final topic of this chapter, variable metric methods. At first, these methods may feel unmotivated. It may not be immediately clear why it is that we are pursuing these complications. However, in the next chapter, in chapter 3, you will quickly see that these methods are utilized heavily in order to derive a wide range of splitting methods. In the analysis so far, the Euclidean metric, the Euclidean norm played a central role. For example, the proximal operator with respect to f was defined using, well here, the Euclidean norm. And also, in our main convergence theorem, in theorem 1, the notion of non-expansiveness, the notion of averageness, was defined in terms of the Euclidean norm. Variable metric methods generalize to the case where we have m norms, rather the Euclidean norm. The m norm is defined as the m norm squared is x transpose mx, where m is a positive definite matrix. Why do we do this? Well, here's one reason. A good choice of the norm m can act as a preconditioner and reduce the number of iterations needed. But for our purposes, the more interesting reason is that sometimes our monotone operator A has a structure, and a well-chosen metric m can cancel terms to make the resolvent with respect to the m norm more easier to calculate. This is something that we will see extensively in the next chapter. And I should make a quick disclaimer. So despite the name variable metric methods, the generalization that we will consider only works with m norms, which are norms induced by the inner product. However, for other metrics, such as the L1 norm, the following analysis does not apply. Let's derive the variable metric proximal point method. If A is a maximal monotone operator and if M is a positive definite matrix, then the congruence transform, M 1/2 inverse A, M 1/2 inverse, is maximal monotone. Here, to clarify, M 1/2 inverse is the matrix square root of the inverse of the matrix M. This operator is maximal monotone, and because this operator is maximal monotone, we can perform the proximal point method. Yk plus 1 is identity plus this operator inverse, so this is the resolvent with respect to this maximal monotone operator applied to yk. And this proximal point method, of course, converges. Next, we can perform a change of variables where xk is equal to m to the minus 1/2 power times yk. And that change of variables gives us this monotone inclusion. So then we take this operator and we invert it. So we get xk plus 1 is equal to I plus m inverse A inverse xk. So this is nothing but the resolvent with respect to m inverse composed with A. So we can write the fixed point iteration in this way. And we can also write this as m plus A inverse times m xk by multiplying out the m inverse. By the way, to clarify, when I write J, the resolvent with respect to m inverse A, I am not claiming that m inverse composed with A is a monotone operator. M inverse composed with A is, in general, not a monotone operator, but we can still define its resolvent through this inverse. This iteration is referred to as the variable metric proximal point method, the variable metric PPM. When we view the iteration through the yk iterates, because this is a proximal point method with respect to a maximal monotone operator, the yk iterates converge to a 0 of this maximal monotone operator. If we translate that result to the xk iterates converge to a 0 of the operator A. The idea of working out the variable metric proximal point method can also be directly applied to derive the variable metric for backward splitting. So let A and B be maximal monotone operators, and let A be furthermore single-valued. Then for backward splitting with this maximal monotone single-valued operator and this maximal monotone operator can be expressed in terms of the yk iterates, and then after performing the same change of variables, we can express the variable metric for backward splitting either in this way. So we have m plus b inverse applied to m minus a, Or we can express the iteration in terms of this resolvent M inverse B composed with I minus M inverse A. The convergence of variable metric for backward splitting can be established by looking at the iterate's iteration through the YK iterates and by establishing that this operator is averaged. The variable metric for backward splitting method has a nice proximal interpretation. So when the operator A is the gradient operator of a convex function f, a smooth convex function f, and the operator B is a subdifferential operator of a CCP function g, then this iteration of the variable metric fbs can be written as solving this argmin. So here we are minimizing the convex function g, and added to that is a first order approximation, first order Taylor expansion of the function f about point x, and then we have a proximal term, but here the proximal term is not in terms of the Euclidean norm, but rather it is in terms of the M norm. So again, the variable metric FPS is the proxgrad method with the M norm instead of the Euclidean norm. If the operator A is beta cocoercive, then m minus 1/2, A m minus 1/2 is beta over the norm of M inverse cocoercive. So the variable metric FBS converges if the metric M satisfies this condition. By the way, in our presentation of the variable metric PPM and the variable metric FBS, we do not have a separate step size, and that is because the metric matrix M absorbs the role that the step size alpha would take. So the matrix M contains the role of alpha. Now when we use variable metric PPM or variable metric FBS, it is useful to define a notion of averageness with respect to the M norm and perform analysis using this notion of generalized notion of averageness. So let's assume that the metric matrix M is positive definite. Then an operator T is defined to be non-expansive in the M norm if, well, it satisfies the non-expansive inequality in the M norm. And for theta between 0 and 1, we say T is theta averaged in the M norm if it is, well, a convex combination of the identity mapping and a non-expansive operator S, where S is non-expansive, again, in the M norm. So these are rather very clear and natural definitions, generalizations of the notion of averageness and non-expansiveness to the case of M norms. In the derivation of variable metric PPM and variable metric FBS, we encountered this type of operator. So M minus 1/2 compose T compose M minus 1/2. Now, non-expansiveness of this operator, this original operator used to derive these variable metric methods, is equivalent to non-expansiveness of M inverse T in the M norm. Well, why is that so? Well, this follows from direct calculations. So non-expansiveness in the Euclidean norm of this operator, it can be expressed, well, directly in this way. This is equivalent to, well, if we perform a change of variables from x to x tilde, so x to x tilde, this is the relationship. From y to y tilde, this is the relationship. If we replace these variables, well, we get this inequality. So this inequality holding for all x is equivalent to this inequality holding for all x tilde and y tilde, because the mapping from x to x tilde and y to y tilde, these are one-to-one mappings. So therefore, this inequality is equivalent to this inequality.